So what we do is we represent a transmission line, not just as one of these circuits, but as a chain of these circuits. So we have a whole bunch of these circuits strung together, each of length delta z, as you can see in the diagram here. We basically want to solve this, and we can solve for V in and V out using our standard circuit equations. We can also solve for I in and I out of one piece of this using our standard circuit equations. And let's go ahead and fix this. This should actually be V sub L, not V sub R. But the voltage across the resistors and the voltage across the inductors, the current through the capacitor and the current through our conductance there can just be given by these equations. This is standard sophomore electrical engineering stuff. And we know that V out is just the V in minus the two voltage drops, and the current out is the current in minus whatever current is going to flow down through there, which is the current through the IC through the capacitor and the current IG through the conductance there. Again, pretty straightforward stuff. I'm not going to solve this circuit. It's tedious algebra to do this. But what you end up coming up with when you do this is you solve for Vn as a function of the position and time along the transmission line, because we want to know our signal both varying in space and time. You find at some length delta z a little bit further, V out and I out are that, and you can see we're setting us up for a standard exercise in calculus at this point. And you come out with these equations right here. You'll notice that what you're doing is you're getting the difference between the voltage as a function per unit length, and you're also calculating your resistance, conductance, inductance, capacitance per unit length. What this ends up with through the magic of calculus is if you let delta z approach 0, you write it as dz. You can let z plus delta z equal z because z is so much bigger than delta z, and then you can effectively ignore it. And this gives you what you call the telegrapher's equation, which are given right here. And the solution of these telegrapher's equations is what we're going to get to by the end of this lecture in solving transmission lines. And this is from the days when we had telegraphs, back when this was the fastest method of communication. And there's a fascinating book, if you ever want to read it as a side, called The Victorian Internet, about how culture changed when the telegraph came along in the 17th century. Excuse me, the 19th century. So now you're bored. I've gone through a bunch of math. I've talked about equation derivations that are given in your book. So why the hell are we going through all this effort just to make life more complicated with a partial differential equation? And this is a partial differential equation because we have variations with z and variations with time in the same equation, which is the definition of a partial differential equation. Fortunately, it's first order. Well, that's what we're going to end with as we get into the last bit of this video. Why are we taking what's a fairly simple circuit element, shrinking it down to zero size, which is what we do in calculus, letting delta z approach 0 so that we can write equations with it. So let's review before we go into this, because we need to know where we're sitting. First of all, we're working with consistent pairs of conductors. They have some spatial symmetry and they don't vary along their length, and we call this a transmission line. We know a real wire has some inductance and resistance per unit length. A pair of conductors separated by an insulator has some capacitance and conductance per unit length. We call this C and G. We're going to model a vanishingly short section of this wire as a simple circuit, which is what we just did before. And we make a long transmission line as a bunch of these circuits strung together. And then we solve these equations basically and come up with some calculus to find the voltage as a function of position and time and the current as a function of position and time along the line. Okay, so theoretically, if we can solve these differential equations, we can calculate the voltage and current at any space and at any time on the transmission line, and thus we can figure out, is it going to act like a circuit element, what's going to happen here, how we deal with these types of transmission lines as electrical elements. What this means. A pair of conductors, transmission line, acts like an electric circuit with resistance, inductance, capacitance, and inductance. The current and voltage vary along the transmission line determined by these equations. Wires aren't just wires when the frequency gets high enough. And so what we've done is we've represented this symmetric structure, the transmission line, here, as the circuit, here. We've gone ahead and written differential equations that tell us how the voltage, V, and the current, I, vary as a function of Z, distance along that, and time. And we've described it as telegrapher's equation right here. Now we do a trick. And this is a really common trick. We do this all the time. We say, assume that the time variation is sinusoidal. It's a sine wave. And you're like, oh crap, here we go again. We're assuming a sine wave. Well, we realized in the earlier lectures that if you solve the circuit for one wave, any wave, you can solve for any signal whatsoever through Fourier stuff. So this is why we make this assumption. We're going to skip through a lot of steps here. You do a bunch of algebra, and you can actually rearrange these equations to give you something that looks like this, two second-order differential equations. And now you're saying, crap, double crap. You just turned what were first-order differential equations into second-order differential equations. Well, two things come from this. First of all, we eliminated time by plugging e to the I omega t in as the time variation. The other thing is this form of the equation right here, where we have a second derivative minus some kind of unknown constant times the original value equals 0 is the wave equation. We're going to see this over and over and over again as we go through this material. And luckily, we don't even have to solve this differential equation. We know what the solution looks like, and it looks like this. What this is it's two waves. One wave is going in the positive z direction as it propagates down the line. So there you go. Those are moving in the positive z direction. The second are waves going in the negative direction down the line in that way. So you have two counter-propagating waves, one going in the positive direction, one going in the negative direction. Each has their own propagation coefficients gamma. And it turns out, if you go through all the tedious algebra, you find out this gamma coefficient includes, as you would expect, the resistance per unit length, the inductance per unit length, the conductance per unit length, the capacitance per unit length, and the frequency. So the propagation characteristics depend on the properties of the line, and they also depend on frequency. And because this is a complex number, we write it generally in this form. And again, you can imagine the amount of algebra it takes to go from here to here, which is why we have calculators and computers. But we write it as a real part and an imaginary part. And now we're almost done. What we find is that the overall solution, when we plug our time equation, remember v of t is equal to v, let's get rid of that, v of z e to the I omega t. When we plug this back into our other solution, we come up with a variation that looks like this. And this is a big, hairy, nasty-looking equation, but it's actually pretty simple because all it is two waves. Wave 1 going that way in the plus z direction. Wave 2 going that way in the minus z direction. We have a variation of phase, and we know it's phase because we've got an imaginary part in the exponential that varies with time and position, and we have some kind of attenuation. So we've seen all of this before. All we need to know is how to deal with this when we're working with a circuit, and that's what the next set of lectures is about. So these equations actually describe something that is an attenuated wave moving along the transmission line. So let's do a little simulation next and see what this looks like, and set it to Bob Marley since it's kind of freaky looking.
Buffalo soldier, dreaded